Hi, I'm Eva. I'm a faculty at the Max Planck Institute for Software Systems, and today I want to tell you about our work towards a sound approximating compiler for numerical kernels. And in particular, I want to give you an overview of the different projects that I've been recently working on with my PhD students and collaborators. So let's suppose that the numerical kernel that we're interested in is a heartbeat monitor that takes as input a heartbeat signal, perform some analysis over it in order to decide whether the heartbeat is normal or not, where in the latter case it may raise a warning or perform some other action. There are many different challenges in implementing such a monitor. However, in this talk I want to focus on one of them, and that is the discrepancy between how we design and how we implement such systems. In particular, quite often in the design, when we focus on the algorithm of an application, we assume infinite resources. This means, for instance, that we assume that inputs are perfect and not noisy, and that we have continuous real arithmetic available. Unfortunately, many of these systems have to be implemented on small resource constraints platforms such as an FPGA, where resources are fundamentally limited, which means that we have to deal with noisy inputs and, in particular, finite precision arithmetic. So there's clearly a gap between how we design and how we implement such systems. And one particular way of bridging this gap is to introduce approximations. However, the challenge is that there is not just one single approximation that works for a particular application. There's many different approximations with different accuracy and efficiency trade-offs. So in general, the more accurate of an approximation we choose, the more we will have to pay in terms of resources, be it memory, energy, or performance. And the particular challenge that I want to focus on in this talk is that navigating this trade-off is hard to do manually, and we would like to automate this. Now, before we go to what we have been doing in this space, I want to give you a very brief overview of the state of the art to put things in context. So clearly, approximations are nothing new and have been, in particular in the domains of embedded systems and scientific computing, a staple since the beginning of computers. However, most approximations in these domains are applied manually, which clearly is costly and error-prone. On the other hand, my work is in the area of programming languages and verification, where one of the goals is to provide automation for many of these challenges. Unfortunately, the techniques here, while providing sound solutions, are still very limited to particular point solutions. So my vision is to develop what I call an approximating compiler that would take as input an ideal real-valued program with an accuracy and resource specification, and then automatically generate an approximate finite precision program that would be guaranteed to satisfy the input specification. So this means that the developer would program as if resources were unlimited, and it is up to the approximating compiler to decide how to apply approximations in order to meet the resource constraints. Now, we're not quite there yet, so today I want to show you the state of our approximating compiler today, and that in particular takes as input a real-valued specification with transcendental functions, and our compiler, called DAISY, generates a fixed point or a floating point implementation with polynomial approximations. So today I want to talk about the different aspects that are needed in order to make this work. And in particular, we will start with how to verify the accuracy of a program with approximations in the presence of arithmetic and conditional statements, and then how to optimize the finite precision and the elementary functions in order to get good resource efficiency. So let me start with the arithmetic. And because this is essentially a bit older work, I'll very briefly give you an overview of what we have, but I won't go into too many details of how we do it. But because the verification is a building block for the optimization, you should at least know what is there. So DAISY takes currently a real valued specification as input. In particular, notice the real data type. So this specification is clearly not executable, so it only specifies the ideal program that we want. In addition to the arithmetic, the user would also specify input ranges that bound the input parameters of the function, And optionally, he or she may also specify an input error. This may, for instance, come from a noisy sensor where you know how accurate that sensor would be. And finally, the developer would specify an error bound on the output that he or she is willing to tolerate. So what DAISY will generate is a finite precision implementation, either in floating point arithmetic, where we simply replace the real data type with double, or in fixed point arithmetic, where this is a particular syntax, so a C code program that can be compiled with the Xilinx FPGA compiler to be run directly on an FPGA. So for those who don't know fixed point arithmetic, it allows you to implement finite precision arithmetic on a platform that does not have a floating point unit. Because essentially what then you have to do at compile time is what the floating point unit would do for you dynamically, and that is specifically defining where the decimal point in your approximation is. So this is exactly what is specified in the AP fixed format, where you provide the total bit length of your data type plus the decimal point. So the main ingredient in order to generate the finite precision codes is a procedure to bound the worst case error bounds on arithmetic expressions. So for instance, for the sine function that we have here, the main challenge in order to compute these error bounds is nonlinear arithmetic. In DAISY, we have several different approaches for how to compute absolute errors, which are defined as essentially taking the difference between a real valued function f, which here is the function body, and its finite precision counterpart, which we denote by the tilde, over a certain input interval. So the input interval is important because in the absence of it, the errors would essentially be unbounded. The base procedure in DAISY performs a static data flow analysis with interval and affine arithmetic abstract domains. Affine arithmetic performs well on linear functions or linear arithmetic operations because it can keep track of correlations, whereas interval arithmetic is sometimes better for nonlinear computations. So we have both available, and both can be chosen depending on the function available. In addition, DAISY provides interval subdivision, which can further improve the round of error bounds. Now you may wonder, absolute errors are not always the best measure for an error. And in fact, a more accurate measure in many cases are relative errors that puts the absolute error bound in relation to the actual value computed. So if you compute an absolute error of 0.1, this may be small if your actual value that you've computed is 10,000, but it is going to be large if the value is on the order of 1. So DAISY does have a procedure to compute relative errors as well, which is not based on a static data flow analysis, but on a global optimization procedure. However, this procedure only works for floating point arithmetic and only if the denominator of the relative error expression does not include 0. Unfortunately, this happens quite often in practice, so for the remainder of the talk, we will focus on absolute errors only, just because they work in all cases. So these procedures are relatively complex. So in order to provide extra assurance, DAISY can generate certificates for a certificate checker written in Coq and Hull 4, so that the error bounds that it computes can be independently formally verified. All right, so that's all I want to say about the arithmetic. For the remainder of the talk, you should know that there is a building block that can compute a worst case absolute error bound on an arithmetic expression. However, programs don't just consist of arithmetic expressions. In particular, they include conditional statements, and they are troublesome when we talk about numerical errors. So let's look at a slightly more involved sign approximation. So here we choose a slightly less complicated approximation when x is less than 1. For instance, in order to save resources, and resort to the more resource-intensive approximation when x is larger. Now the trouble with this function is that the control flow may diverge. For instance, in real arithmetic, we may take the if branch, but due to errors, the corresponding finite precision execution may take the else branch. So they're essentially taking different branches, and if we're computing a sound error bound, we have to account for this discontinuity error, as we call it. So in particular, the error bound that we want to compute is between f1, computed over the reals, and f2, with the tilde, computed over finite precision arithmetic. Now, bounding this error is challenging because of the complexity of the constraint. In particular, we're mixing a real valued function and a finite precision function, which both are tightly correlated. So our key insight in approximating this error is that we want to break up this total error into different manageable pieces, and in particular in 3 pieces, where the first one, or the middle one here, captures the real valued difference. So we're only computing the difference between 2 real valued functions. Then the round-off error on the finite precision execution. And then we want to bound the difference on the real valued function due to the initial error, which we can capture by computing the Lipschitz constant. So breaking this total error into the different pieces clearly loses some accuracy. However, in return, we can actually compute tight error bounds. However, this approach is not quite going to work for the initial example that I talked about initially. So let's go back to our case of something like a controller that makes a discrete decision. And for this, I'm going to use this rigid body example where we have 3 inputs, all bounded between -15 and 15. That performs some computation, and based on this computation, it may, for instance, raise an alarm or continue execution. Now again, the problem is that in reals, we may have to raise an alarm, but due to errors in finite precision, we just continue as if nothing happened. So let's put the raising alarms, let's put the return values into 0 and 1 and back into the numerical case, so we can actually do a numerical analysis. And then if we perform a worst case analysis, we will have to essentially say, trivially, that the maximum error is 1. In general, there will always be some input error, so in the worst case, we will always make the wrong decision and return the wrong number. Clearly, this is not very helpful. So actually, the question that we should be asking here is not about the worst case accuracy, but it's how often the program returns the wrong answer. So this necessitates a probabilistic analysis in order to answer how often we get something. So this means we have to now take into account not just upper and lower bounds on our inputs, but probability distributions. Since not all inputs are usually equally likely, and they will also not equally likely propagate to a result that would cause a divergence. So if we run a simulation, we can get the probability distribution on the value res, which can then give us some idea about how often we may take the wrong decision. Now, obviously, we don't want to do this with a simulation. We want to have a sound analysis. And in particular, the goal of this work is to compute the wrong path probability. That is the probability to compute the wrong answer, in this case, a 0 instead of a 1, or vice versa. Now, in fact, we can encode the wrong path probability as a probabilistic program. For instance, in the syntax of the PSI solver, we can define x1, x2, and x3 as Gaussian, as normally distributed between -15 and 15. We can encode the numerical computation, and we can compute the worst case absolute error bound with DAISY on the value of res. Now, this then gives us the interval around 0, around the decision variable, where we may potentially take the wrong branch. So we can encode this wrong path probability and compute the exact expression for it using the PSI solver that was presented at CAF 2016, which give us a very long and complicated expression that we can then solve numerically using Mathematica with a guaranteed precision. So this is nice. This is the exact value for the wrong path probability. Unfortunately, for non-trivial examples, this approach simply times out. So the exact approach doesn't work, so we'll have to do an approximation. And in particular, what we will do is we will take the input probabilities and we will discretize them into so-called P boxes. So in particular, each of these boxes has a lower and an upper bound and a weight, which means that the value is between, say, A1 and B1 with probability W1, and between A2 and B2 with probability W2, and so on. So clearly we can determine the accuracy of this over-approximation by varying the number of subdivisions. More subdivisions will provide us with a more accurate estimate of the probability distribution, but it will also be more costly. Then we need to propagate these distributions through a program, which, when our variables are independent of each other, simply reduces to interval arithmetic. However, when the variables are dependent, we have to solve an LP problem and also track the dependencies between the variables, which we do with affine arithmetic. So I do not want to go into more details. The gist of this is we can approximate a probability distribution with varying accuracy. However, the propagation of this can be quite expensive. So let me give you an overview of how we compute the wrong path probability. So we start with our input program and first perform a round of error analysis in order to get the absolute error on the decision variable. Then we take the input distributions on the input parameters, perform our probabilistic analysis in order to get an approximation of the value of the decision value. And then we compute an intersection with this error bound. So let me show you this pictorially. Suppose that this is the output distribution that we have computed. And suppose that we're comparing the result of the numerical computation against 0, as was in our example. Now, if you have an error of approximately 0.2, this means that all the values that fall between 0 minus 0.2 and 0 plus 0.2, so 0.2 around 0, are potentially susceptible to taking the wrong branch. So in this case, then we have to check which boxes actually fall into this interval. And in our example, this would be the boxes with the weights W1 and W2, which means that the wrong path probability is W1 plus W2. So this analysis finishes in reasonable amount of time. Unfortunately, it computes a wrong path probability of exactly 1. So this means the probability of taking the wrong branch is 1. So that's again not particularly helpful. What we have observed is that the over-approximations committed by the approximate probability propagation are quite large. So we reduce this by subdividing the input interval into smaller subdomains and running the probabilistic analysis on each subdomain separately. In addition, we have observed that not all of the input domains can even reach that critical interval. So we can actually disregard these. You do a reachability check, and if the critical interval is not reachable from a particular input domain, then we completely exclude it from the analysis. Now, our probabilistic range analysis with subdivision now finally computes a wrong path probability of around 7%. So that is a much more reasonable value than 0. So this was just one particular example. We've run it on more examples. Our analysis on each of these runs on the order of minutes. The complexity of these is roughly what you have seen in our rigid body example. It is sensitive enough to compute different wrong path probabilities when the inputs are differently distributed. So in particular, if the inputs are normally or uniformly distributed, we compute different probabilities as expected. but it also means that the over-approximations are small enough that we can see the sensitivity. We've also checked the over-approximation on the few examples where PSI actually does return in time, and we see that we have an over-approximation of about 1 order of magnitude, which in this context I think is quite modest. So this means we now know how to verify the accuracy given some approximations. Now let's see how we can use this in order to actually optimize a numerical kernel for efficiency. So the first approximation we consider here is finite precision, which approximates real arithmetic. And in this context, we want to assign choose a particular finite precision. So let's suppose we again have our rigid body now without the conditionals for simplicity, and that the user has specified an error bound of 1.75 to the 10 to the minus 13. Now it turns out that uniform double precision is just not enough in this context. Using double precision, DAISY computes an error bound of 3.5 to the 10 to the minus 13, which is just a little bit too large. So if we stick to uniform precision, then the next higher available precision that would satisfy this error bound would be quad, so that's double precision. This clearly satisfies the absolute error bound by a huge margin, but is also significantly slower than double precision, especially because it has to be implemented in software. However, it turns out that we can use mixed precision, so choose different precisions for different operations. And in this case, this will satisfy the absolute error bound and will be around 28% faster than uniform quad precision. So in particular, we can have 3 arithmetic operations that are performed in double precision and 4 that will be performed in quad. Now, clearly, we don't want to do this assignment of precisions to arithmetic operators manually, so we want to do this fully automatically. And the challenge here is that the search space is very large, but also very complex. Because of this complexity, we perform an incomplete search guided with our static error analysis and also a static cost function. Our error analysis is sound, so whatever mixed precision our algorithm chooses is guaranteed to satisfy the error bound. However, the algorithm is not guaranteed to return the optimal, that is, most resource efficient implementation. So I want to give you an overview of how our incomplete search works, and it is based on delta debugging that was also introduced in the tool Parsimonious before. And in explaining this algorithm, I'll use these boxes with the numbers. Each box represents a set of arithmetic operators, all in 1 precision, in this case all 28 bits, so quad precision. So initially we will assume that all of the arithmetic operations will be performed in a high precision, so say 128 bits. And then we'll check the error. If it satisfies the round of error bound specified by the user, then we can continue with our optimization. The first step is to check whether we can lower all of the operations to a lower precision, in this case 64 bits. If this is not the case, it means that we have to find a precision assignment somewhere in between. So we will split the set of arithmetic operations into 2 and lower one part of it to a lower precision and leave the other half in the higher precision. Let's suppose that this still does not satisfy the given error bound, so we will continue with our subdivision until eventually we find an assignment that does satisfy the error bound. And then we will use our cost function in order to choose the one that will have, hopefully, the better performance. So for the static cost functions, we have empirically evaluated a number of them and found out that if you have only single and double floating point precisions available, then the best is to use a cost function that we call benchmarked, where we have run individual arithmetic operations and benchmarked their relative running times and devised the cost function based on these numbers. If you also have quad precision, which is as I mentioned, implemented in software, you can actually get away with a very simple cost function where you, for instance, assign cost of 1 to single precision arithmetic, a cost of 2 for multiplication, and then a much higher cost for quad. For fixed point arithmetic, we have 2 cost functions available. One is based on the area, so this is directly based on the number of bits that you need for your implementation. And furthermore, we have one that we have used machine learning for that estimates the performance. The reason why we have to use machine learning here is that we assume that the generated code from DAISY will be run through the Xilinx compiler, which generates FPGA code, but this compiler is essentially a black box of which we have to estimate its behavior. So we use machine learning for that. So in all of this, we have implicitly assumed that the order of operations is fixed. As you probably know, finite precision arithmetic is not associative, so choosing the left-hand side or the right-hand side here will give you different results. And this also means that it will commit different errors. Now what we want to do is find the computation order which incurs the smallest round of error over the particular input range that is specified, and that is equivalent under real-valued semantics. Now doing this is nice because we can do this once at compile time and then have smaller round of errors at runtime essentially for free. Again, doing this manually is not feasible. Doing this automatically is challenging, again, because of the very complex and large search space. So yet again, we resort to an incomplete heuristic algorithm. However, this time we found that a genetic algorithm performs particularly well. So I want to give you a high-level overview of how this algorithm works. So we start off with 30 copies of the initial expression that we would like to optimize. And we will call these 30 expressions the population, which we will evolve iteratively. So in each iteration, we will pick candidate expressions that we will mutate based on the standard associativity, distributivity rules. We will evaluate its fitness using our static round of error analysis, where the idea is that a smaller error is better and will make the expression more fit. And then we will use these round of errors to have a heuristic with which we can pick better expression for the next population, for the next iteration of the algorithm. Now this algorithm is not greedy, so even expressions with a slightly larger round of errors still have a chance to get into the next population. However, the chance is smaller, so fitter expressions are more likely to go on to the next iteration. And we have found that in this domain this was particularly effective, and on our benchmarks we can get significant improvements in errors, so we can improve the errors that we can prove by up to 70%. So to back up, I've shown you our rewriting and our precision tuning optimizations, where the rewriting improves the error and the mixed precision tuning improves the performance. Now they strongly suggest that we should put them together to improve performance even more. The idea is that the rewriting will improve the error and give us a somewhat larger budget for mixed precision tuning so that we can ideally lower some more operations into a low precision. This indeed works. So on our running example, we can now have 4 operations instead of just 3 in the lower double precision and 3 in quad, which means that we have now an implementation that is 43% faster than the uniform quad precision. If you remember, our original implementation was only 28% faster than uniform quad. Now, if we again run more experiments and compared also against the state-of-the-art FP tuner tool, and we have also added sort of manually a rewriting step to FP tuner as well. So just to give you a high-level summary of our experiments, for error bounds where single precision is just not enough, so that your under uniform precision, you're forced to use double floating point precision. Our mixed precision tuning can give you up to 20% savings in performance with respect to a uniform double implementation. When double precision is not enough, so you would have to go to quad, we can get up to 60% savings, which is much higher because quad is implemented in software. And we have also found that using rewriting is generally helpful also for when applied to FPTuner. Now we can also see that FPTuner for when optimizing 64-bit versus quad precision improves the performance more than DAISY, though not for the single versus double case. The reason is that FPTuner does its optimization based on global optimization. However, this optimization is also expensive, so DAISY scales somewhat better. These experimental results are for floating point arithmetic only because this is what FPTuner supports, but I want to mention that DAISY also supports this optimization for fixed point arithmetic. And we will see that just next because we will use it also to optimize elementary functions. So far we focused on just arithmetic. However, many numerical kernels will feature elementary functions such as sine and cosine. These are usually implemented in library functions, so are easy to use. However, these library functions provide only a limited choice in precisions. For instance, only 32 or 64-bit floating points. And in particular, when we want to run this on an FPGA in fixed point arithmetic, the fixed point implementations are inefficient. So for instance, the Xilinx compiler provides a library of elementary functions. However, only some of them have fixed point implementations, and some of them then transform into floating points, compute the transcendental function or elementary function in floating points, and then transform back to fixed points. So this is inefficient. Our goal is, in this particular project, is to synthesize polynomial approximations that are specialized to the particular use case and are thus much more efficient. So in particular, we can use the fact that the inputs, in this case x, y, and theta, are bounded within some relatively small ranges. So we need not provide a completely general implementation of sine and cosine as a library function does, but we can specialize to a particular input domain. Furthermore, we want our approximations to have a guaranteed end-to-end error bound. So in particular, we do not want to have an error bound only on the individual sine and cosine functions, but at the end on the result. And we would like to do this in fixed point arithmetic because this gives us even more optimization possibilities. Now, the main challenge towards this goal is to distribute the error budget. So let me explain what this means on our high-level algorithm. So the user specifies an error bound at the final result. However, this error needs to be essentially distributed between the polynomial approximations and the arithmetic of the original function and the arithmetic of the individual elementary function approximations. So our algorithm will first distribute a global error budget towards each elementary function, and then for each elementary function, distribute its local error budget between its polynomial approximation and the fixed point arithmetic approximation. So how do we distribute the global error budget? For this, we can reuse our mixed precision tuning that I've explained earlier by assigning a precision to each arithmetic operation and each elementary function call. So the key idea for why we can use mixed precision tuning here is that we can treat elementary function calls as if they were some special arithmetic operations. And then the error associated to a precision that has been assigned to an elementary function call, we can then transform this into essentially a local error budget. Now, the idea why the reason why this works is intuitively you do not want to have the elementary functions implemented with much more accuracy than the arithmetic itself, because otherwise the arithmetic error will dominate the elementary function call error, and in that case you could have just used less precision for the elementary functions. So in summary, the arithmetic operations and the elementary function calls should have roughly the same accuracy, otherwise one would dominate the other. Now the mixed precision tuning requires some kind of cost function because we're optimizing for performance in this case. However, at this point we don't know yet what approximation we will have for the elementary function calls. So this means that our cost function is essentially abstract, and empirically we found that assigning roughly twice the cost of an arithmetic operations to elementary functions works well in practice. So once we've distributed the global error budgets, we have a local error budget for every elementary function, and then we need to distribute this between the polynomial approximation and the fixed point arithmetic approximation. We do this distribution with a feedback loop. So we first try to split the error budget equally, and then we run the polynomial approximation, the fixed point arithmetic assignment. We check the cost via a cost function, and then we try to either increase or decrease the approximation budget. And iteratively, we then find the best distribution. So how do we do the polynomial approximation? For this, we use the tool MetaLibM, which is a generator for piecewise polynomial approximations. Internally, it uses a Remes algorithm, which is guaranteed to find the best polynomial approximation for a given polynomial degree. It performs piecewise approximations, so it automatically splits the domain so that you can, for instance, as in our example earlier, you can have a more efficient, less complex approximation for one part of the input domain and a more complicated one for the remainder. However, MetaLibM generates only double precision floating point implementations. So we still have to assign the fixed point arithmetic ourselves. For example, for our sign call, for our running example here, this is the function that MetaLibM would generate. So it generated two different polynomials for two input domains. And then we used again Daisy's mixed precision or uniform precision assignment on each polynomial approximation to get the actual finite precision implementation. So we've evaluated this approximation on a number of numerical kernels, roughly on the same complexity as you have seen so far in this talk. And we're comparing here against a baseline of using the standard library functions together with the Xilinx library. And what I'm comparing here is the number of cycles the generated FPGA code takes with our approach with respect to the baseline. So the lower is better. 1 is exactly the same number of cycles. And you can see that for most of the benchmarks, we outperform the Xilinx standard library approach on average by 45%. Now, there are sometimes error differences whether the input, so the target error bounds, whether they are relatively small or relatively large. Though this is mostly for 2 of the benchmarks. Now, the outlier here is the Gaussian benchmark. We suspect that this is due to the fact that this benchmark has, I think, 5 log functions, where our approach generates an approximation for each log function separately, which turns out to be quite inefficient. However, this is something that we plan to improve on in the future. So with this, let me finish. I have given you an overview of what our approximating compiler DAISY can do today. In particular, it can take real-valued specifications with transcendental functions and generate fixed point or floating point implementations with polynomial approximations that are guaranteed to satisfy a user-given error bound. So this sounds all nice. So what's next? So the next big challenge in this line of work is to increase the scalability. Thank you very much for listening. And if you have questions, then feel free to email me or drop me a note wherever this video will be uploaded.